The talk's actually about the El Nino, but I put this up because a lot of theories, or a lot of people, when they talk about the El Nino, talk about equatorial Kelvin waves as carrying heat across the Pacific. Now, equatorial Kelvin waves are gravity waves, like these are. And I don't know if you ever tried swimming in one of these or surfing in one of these. What you find is that waves carry a lot of energy. I mean, if I'd had the sound on this, it's quite noisy. And they also can carry quite a lot of momentum. If you try and stand up in the waves, you can get knocked over, and usually in the direction that the waves are going. But what they're not very good at is moving stuff. And if you're surfing on one of these and you fall off, you'll stay where you are. What you can see on this is that the bubbles, once they form, don't move very far. So although they look dramatic, and they've got a lot of energy, and they've got a lot of momentum, when it comes to moving people, bubbles, or heat, they're pretty useless. That's going to be one of the points of this talk.
So David Webb will give us a seminar on the modeling of El Nino events.
Okay, we'll do that. Our people will be turning up soon. So that's the background to this, is that there's this theory that's put across quite a lot, that westerly wind bursts in the Pacific drive equatorial Kelvin waves, which somehow or other move heat across the Pacific and cause the El Nino. And there are various other theories. I mean, some people say, oh, the waves slosh across the Pacific, and that carries heat. But if you've ever been in a bath and you slosh water backwards and forwards, you find the rubber ducks always stay at the same end of the bath. I mean, sloshing doesn't move heat around. There is another theory that people come up with, and they say that the winds in the Western Pacific, they're from the west, they drive an eastward flowing current, and that takes the heat. But as we'll see later on, when there are winds in the West Pacific which are driving the current towards the east, there's equally strong winds in the easterly Pacific pushing. And so there's no reason why the westerly winds should win. So whatever theory you agree with, there's a problem. And one of the things to do, well, what I want to do is actually look at this problem in more detail and try and come to a solution. So we're going to talk about the El Nino. It's going to be from the point of view of the model Pacific, from a model Pacific. So from that point of view, it's what I'm going to put forward are just hypotheses. But they're fairly strong hypotheses, and I think that most of them will actually turn out to be true for the real ocean. And two of the key figures is the sea surface temperatures. I'm going to be looking at the very strong El Ninos of 1982-83 and 1997-98. The strong El Ninos are the ones that first got people interested in the fisheries off Peru disappeared. And so we're really looking at events that get right across to the Eastern Pacific here. And the main feature that turns up in the model in both of these periods, 1992 and 93, is the difference between the years before, up here, where temperatures tend to be greatest in the Western Pacific, and the North Equatorial Current is it's a strong current, but it doesn't do very much. And yet in an El Nino year, this takes heat right across the Pacific. And this is in September each year. What you tend to find of the strong El Ninos, they sort of start during the summer months. The heat gets carried across the ocean during the autumn, and they arrive in the Eastern Pacific around Christmas, when some cynical fishermen call them the Christ child El Nino. And I think that must be a very cynical comment. Anyway, because they can lead to starvation. So now what I'm going to do is, because I've got quite a lot to get through, I'm going to start with the main take-home message from these. And what I'll then try and do is go through the background and try and convince you that this is the case. This is a strong El Nino. You find that most of the heat is being carried by the North Equatorial Counter Current, not by things along the equator, although there is this feature here, and there is a current in this direction along this part of the equator. But most of the heat is being taken further north. And this is the region of the intertropical convergence zone. If you're looking for deep convection in the atmosphere, it'll be along a line here, or it'll be on a line down here with the north and south convergence zones. Now this also shows where the, it shows roughly the line of the North Equatorial Counter Current. It tends to start fairly close to the equator in the west, and as you go eastwards, it moves further away from the equator, and we'll come back to why that is later on. So, in terms of the El Niño mechanisms, what the model is showing is that it's the NECC, which is the main agency in carrying heat to the east. It's a geostrophic current, it's in geostrophic balance, it's not a gravity type wave or anything of that sort. The other key thing is the role of tropical instability waves. You'll notice here we've got strong tropical instability waves extending even into the Western Pacific. They've disappeared in this region here. And what we'll find is that these are very good at mixing heat in and out of the NECC. In fact, they're what's cooling it down in this region, whereas here, when they disappear, the NECC can take heat further east, and it can start new areas, deep convection, further east. The other thing is that why were these, well, you have a current here which is running each year, and the real question is why don't you get an El Nino each year, or why don't you get the NEC carrying heat across the Pacific each year? What's so special about these strong El Nino years? And the key thing there appears to be the annual Rossby wave. This is a Rossby wave which starts in the spring. Winds in this part of the world reduce sea level in this region. Waves at different speed travel across the Pacific. The ones nearest the equator get over here this starts early in the year. About midsummer, they're getting to the West Pacific, where they're causing quite a strong NECC at this point. And you have other waves at high latitudes traveling more slowly. So this front tends to have this sort of slope on it. So those are three mechanisms I want to put forward. But there is a second take-home message. And this is not my work, this is somebody else. And it's to do with deep convection in the atmosphere. The idea is that the ocean has to take heat across the Pacific, and it has to be hot enough that it's actually going to produce really deep convection in the atmosphere going up to 40, 50,000 feet. Now this shows the temperature contours in the atmosphere from something like 270 degrees and 300 degrees, and it's called the wet adiabatic. Water with sort of 100% humidity down here at roughly 30 degrees will have enough heat in it for the clouds to actually go right up to, and this corresponds to 14 kilometers. So right up to the top of the atmosphere. If the temperature is too low, if it's a few degrees below that, the convective clouds just can't get up high enough. So you're only going to get deep convection if your temperature's above 300 Kelvin, so that's getting on for 30 degrees centigrade. Anything below that, forget about it. So it's a switch. People tend to work with anomalies when they're talking about temperatures affecting El Nino. Anomalies are no good enough. You actually have to have, it's an on-off switch. It's got to be hot enough for something to happen. So this is the work that another group has done, looking at it's the temperature at the top of the clouds against the temperature of the ocean surface. This is cold, so this is essentially the high clouds going up to 14 kilometers or so. The little dotted line here is the number of events they're finding. And what they actually conclude is that in order to get deep convection, you've got to have 27.5, 28 degrees or north or more. This is work done in the Atlantic and Indian Oceans. They didn't do much in the Pacific, but these show some temperatures required around Australia in order to get deep convection in the dry season, and the red ones are the wet season. The wet season, you see, you've actually got to get above 30 degrees or so, or around 30 degrees in order to get deep convection. So it's important to get water that's warm enough across the Pacific, not just get heat across the Pacific. Now, you should all know about El Nino. This is put in for the people who don't know the background. This actually, I've included, it's Vertke, who did some of early work in the region, and we'll come to his work later on. The atmospheric theories start with Cherkinis. I'm never quite sure how to say it. But what I want to show here is a sort of typical picture you'll get on the web, showing convection going from Southeast Asia to the Central Pacific. Only trouble with that is that there is never any convection in the Central Pacific. The convection is either north of the equator in the ITCZ or south of the equator. The equator itself has essentially no deep convection. And so essentially everything that's based on what's happening just on the equator that you see on the web or anybody else talks seems to be incorrect, let's put it. And that goes to the atmospheric people measure their El Ninos by the temperatures in these areas. 1 and 2 was the original oceanographic El Nino region. Ones they're keenest on is this 3.4. It's the region between 5 degrees north and 5 degrees south. And most of the work has been done defining an El Nino in terms of what happens here. But deep convection regions are occurring up here, or they're occurring down here. And I have a problem with the atmospheric literature in that I cannot find a good review of what is happening to convection in this region, which as an oceanographer I can use. There seems to be something seriously wrong with the literature. Anyway, I'm going to talk about the NEMO 12th degree ocean model. This is the one I used. Andrew had a run of this model, needed analysis. I thought it was about time I did something for the group. And so I decided to have a look at validating it, just checking it against observations. Most of you would have known about that. The first bit of the work was actually to do this validation. And what this shows is for these regions I've talked about, what the model does, which is the thick line. So the reds are region 4, greens are 3.4, 1 and 2 at the bottom. And how those temperatures vary with time, this is from 1980 right through to 2010. And in it you can see the strong El Ninos. This is the one here in 82, 83, and the one here in 1997, 98, which I'll be concentrating on. And the light lines are what the observations show. And although there's some discrepancies down here, you find that at the time of the strong El Ninos, there's extremely good agreement between the model and the observations. So much so that I didn't believe it. It wasn't my model, it was somebody else's model. So I thought I'd check it through. And I looked at all the idea is, what I was concerned about is that the actual sea surface temperatures were affecting the atmospheric temperature. These people are assimilating atmospheric temperatures into the ECMWF model. So we get a sort of sea surface temperature in the atmospheric model data used to force the ocean model run. And having the the atmospheric temperature right could force the ocean to have the right temperature. So what I made sure is to find out whether in these regions the atmosphere was heating the ocean or cooling it. And when I did that study in this region, this is the net amount of heating, and you find it's actually cooling the ocean more than, not more than usual, but there's no evidence of heating. But, you might expect that if there was heating here, this black curve here would become positive during that period, but that's not the case. So the model seems to be doing well. So we can, on that basis, we'll use it to actually study what's happening. So this is quick showing some of the output for the model, the sea surface elevation. And this is interesting because it shows the value that you get along in sea surface along the equator. You have a current towards the west, geostrophic balance. You have to have increase of pressure as you go north and you go south. You get this second valley, which is generated by the Ekman suction in this region, generates velocity waves going across, and this gives you a geostrophic flow around this valley. On the south side, it's the North Equatorial Counter Current. North side, it's part of the main gyre. But there's a key thing in that as you go from this point to this point, sorry about jumping around, the Coriolis term is varying by about a factor of 2. So that means that for a given pressure difference on the north side, the on the south side, you're going to have twice the current. So that, you know, your NECC current tends to be much stronger than the counter current further north. Yes, sorry, this is part of Mexico down here. And you've got what you can't see is Australia and China. But, okay. And these are the temperatures. We're only going down to 300 meters. It really shows how very shallow all of these systems are. You know, you're used to maybe working with about 2,000 meters of ocean. Here, 300 meters is deep. Quick Equatorial Pacific, I shouldn't have to show this to you, but what I wanted to show, again, the warm, looking along the equator, the warm core is actually very shallow. This is the equatorial undercurrent. Starts, increases, stops. This is effect of some of the islands' ridges. I think it used to be called the Gilbert and Ellis Islands, but I'm not sure what it is now. But essentially the transport through there is fairly constant. And if I look at sea level, you get the average during the year is you've got this trough due to the Rossby waves, and you have the equatorial trough as well. And looking across the equator, again to give you a rough idea, you've got the Ekman suction at the equator bringing water up. You've got two warm cores, north and south. If you look at the north-south velocities, you've got the Ekman transport away from the equator, north and south. There's winds blowing from the east all along the equator as the southeast trades, and that causes this. And you get some return flow, geostrophic inflow underneath. The velocity east, equatorial current, actually two cores, equatorial undercurrent, and this is the North Equatorial Counter Current. Again, going just down to about 150 meters or so, but just at the depth that these features can take heat across and sort of cool it, or not cool it. Talked about those measures of the El Nino along this plus or minus 5 degrees. What I've done here is produced a Hofmuller diagram going from 1980 through to 2000 of the average temperatures of each longitude here. And the strong El Ninos turn up as this sort of event which suddenly shoots across the whole ocean. And we have various other El Ninos, which these mid-Pacific El Ninos, if you look at this temperature thing, it sort of stutters up, it increases a bit and then wanders back a bit and increases a bit and wanders back a bit. It's not a sudden event like this, it's very much almost something, a random walk. What I want to do today is to indicate that there's a likelihood that the physics behind this is somewhat different to these very strong events. If I look at the rainfall, as I said, there's not much rainfall on the equator, so we have to go to 12 north to 12 south to actually start seeing the signal. And again, you see the very strong signal during these strong El Ninos and the rather weaker events, the rainfall events that occur at other times. I've compared here this 1980-85 period with 1995-2000 and a coupled one that Andrew's been involved with. And what I wanted to show is that all of these events have some sort of similarity. You see the tropical instability waves, that's what these things are. There's some sort of annual signal, but these things, the main events start roughly in the summer in the Western Pacific, come across and get across around Christmas. This is a little bit odd in that there seems to have been one of these weaker El Nino events started first, and then come the summer, one of these strong El Nino events went all the way through. The atmospheric one is not so obvious what's going on. Now, I made this point that the NECC has to transport heat that's warm enough. So what I've started looking at is the temperature, volume of water carried with temperature greater than 28 degrees crossing various longitudes. And if it's cooler than 28 degrees, it's a waste of time. So the idea is that larger volumes of warm water here will actually trigger deep convection further east. And what you find is that during 1982, the El Nino lasted for 2 years, but essentially grew during 1982. During 1982, you have this much stronger than normal. Well, it's not so much stronger than normal, but it's carrying more heat than normal during this period of the year. And the total volume is very large. There is some heat carried along the equator right at the end of the year, but that is much smaller. So in terms of the heat transport, well, the transport of really warm water, is the North Equatorial Counter Current is winning hands over the equator. I've also looked at various other longitudes. The picture is slightly different, but again, you have this effect that the NECC is the main thing, and you sometimes get some event on the equator later on. I'm not sure if it shows up on this, but there's another feature. Yeah, there is a slight tendency. You'll see the NECC is usually about 6 degrees, and what you find is these strong events tends to move down to about 4 degrees. So it's actually moved further to the equator. Again, the Coriolis term is smaller. Right, so changes during an oceanographic El Nino. How are we doing? Not too bad. Main current, well, in a normal year, you get a lot of eddy events going on. During a El Nino year, or during the development of El Nino year, most of it is along the equator. That's just really a summary slide. What I was interested in is really why this was so different. And as I said, I mean, first of all, I thought that it was maybe the winds in this region dropped. If you look at the wind along the equator, or at 60 north, they are small in this region. So that would indicate that the Ekman transport had dropped, and maybe that was what was affecting the heat content. And so I had a look at that first. And what I've done here is plotted the wind stress at 6 degrees north. That's sort of where we're interested in, is the cooling of the NECC. And you find that during this period, there is a drop-off. While we've got the warming crossing the ocean, there is a drop-off of the winds, and you do get this period of westerly wind bursts that occur later on. But during this time, at 6 degrees north, you've still got some effects further. Especially true at the equator, we'll see that the easterly winds continue. But just at that point, which is a fairly typical one, we're finding that Ekman transport is dropping to zero during part of the year, or during the second half of 1982. So having the low winds, again, is going to, it means that any cooling during the Ekman transport has disappeared. I looked at then tried to have a look at the geostrophic return flow, and what I've done is produced a pressure integral, and you'll have to just believe me that that gives the pressure integral down to about 300 meters, and you have to believe me that gives me some measure of the geostrophic inflow. And what you find is it's the slope of this gives you the geostrophic inflow, and if I take the average slope, that roughly equals the average Ekman transport, that you're away from the equator here. During the second half of 1982, this doesn't disappear completely, but you get this Rossby wave coming in. You can see these sort of Rossby waves each year, but the annual Rossby wave this year appears to be a lot stronger. And that does tend to reduce the geostrophic inflow, but you've got odd things going on. It's obviously greater just at this point, and you've got a reverse flow just there. So the geostrophic inflow maybe is not affected so much, but that is deeper in the ocean. From here, you can see the tropical instability waves, their effect at 6 north. The gradients here give you some idea of what the transport is in the tropical instability wave. And what I've done here is actually, I've done an averaging, worked out what the gradients are here, averaged them, and I plotted them in this figure here. And you can see that the values of the transport by the tropical instability waves is quite large. We've got a current, the North Equatorial Counter Current. It's about 20 sphere drops, so it's as strong as the Gulf Stream. I think that's right. It sometimes goes up to 40 sphere drops. It's quite as strong as the Gulf Stream. And yet we've got these instability waves, which essentially they're taking water north. They've got 5 sphere drops per degree of longitude. So if you go over 5 degrees of longitude, and same on all of those, you've got 25 sphere drops, which is more than the normal transport in the NECC. So the tropical instability waves can mix water in and out of the NECC much more rapidly then the NECC can bring water in from the west. So that seems to be the main reason that the NECC is cooled off. And you can see that during this 1982, and also during 1983, but during the key region is during this growth period here, the tropical instability waves essentially dying out, as we said, and so there is no mixing. That's the total transport. So when I say the NECC transport is 20. Yeah, I think that most of this transport in the tropical instability waves is light water. If you look at the figures in a normal year, it's sort of, you're bringing cool water up from the equator, below 28 degrees. Yeah, they're taking cold water north and they're bringing warm water south to the equator. Yeah. Well, no, this is what I've got here is essentially the noise on this picture here. Okay? From this pressure gradient, I can work out the actual northward geostrophic transport at any point. I then calculate the RMS average over some sort of small region, like that amount. Okay, and that's what's plotted on that side. Okay. Now another test of this is to put in particle tracking. And what I've done here is I've chosen a region in mid-ocean, this starts in June. Temperature here was greater than, typical year, I couldn't use 29, I had to use 27.8, so I took 20.8 here and saw where the particles went. And this is where they went in the rest of the year, going from midsummer through to the end of 19. You see most of them, some of them get swept back in the equatorial current, others get swept into the main gyre there. Very few of them finish up in the Eastern Pacific. But in an El Niño year, when it's growing and we've got all these processes going on, these particles, most of them get right over into the Western Pacific. Sorry, the Eastern Pacific, north of the Galapagos. So, essentially that is showing that the mixing processes are much reduced during these strong El Niño years. Because I was also thought I ought to check what is going to happen with this particular blob of water. We've still got winds coming in this direction. You can see the upwelling that's being incurred, and you've still got some instability waves. We've got westerly winds here. We tend to get sea level high in this region, but let's start with some water in this sea level high, see where it goes at the end of the year. And it did go some way, but quite a lot of it came back. So, that water didn't get us anything like so far. And it's certainly, what you find is that this is along this line here is where the intertropical convergence zone is. And there is evidence that that actually moves down to this line during an El Niño period. Yeah? That's it? Yeah. Yeah. I think it does, yeah. I'm not sure. Sorry, look, don't know everything. You may well be right. It'd be worth comparing it with your observations. When I've been comparing, I've started looking at comparing with satellite data, and I do tend to concentrate on this area. I'm not concentrating what's happening. Yeah, okay. I mean, one thing that comes out of this is don't believe what you're told. If you can, go away and check it yourself. Right, so I think we've been through all of those points, and I'll move on. So why did it start in 1982? Why was it stronger? So this actually takes us back to Bertke, who, in one of his first papers, when they were working off Peru, looked at sea level at these two islands and found that when an El Nino was on, the sea level difference here was large. And he reckoned that was due to the North Equatorial Counter Current was being very strong. And he wrote this in a paper. But if you read the paper, and I guess the reviewers got to him because it was the time that equatorial Kelvin waves came in, he sort of, pulls back and he says, oh, it might be equatorial Kelvin waves after all. And from then onwards, everybody sort of thought that, Bertke thought that equatorial Kelvin waves caused the El Ninos. But actually, he'd done this initial work, and it is quite convincing that there is the strong correlation between the sea level differences between these 2 points. That's essentially on the equator and in that trough, and the strength of the NECC. And if essentially what he was saying is that you're getting some Rossby wave coming through. It's dropping sea level at this point, and that's has something to do with the El Nino. And so I've been looking at that in a little bit more detail, see how true that might be. What I do is look at, go back one, plotted Hofmüller diagrams of sea level along the equator, sea level at 6 degrees north, which is sort of along the line of the NECC, and sea level at 9 degrees north, which is roughly in the center of the gyre, or the deepest part of the gyre. And these are the figures here. On the equator, you tend to have reasonably high sea level. In the west, dropping off as you go into the east, this is where Ekman suction is reducing sea level. Once the winds start blowing, you do get this lump of water in the central Pacific. You've got westerly winds here, easterly winds in this region. But you do have this, you can see this trough going through, signal. And so what it means that at this time there is a very strong grade in the West Pacific. There's a very strong gradients in sea level between 6 degrees north and the equator. So that's actually going to drive a very strong geostrophic current. You see as you go at 9 degrees north, things don't change. So if you say, well, the total sea level difference is what you're getting between here and the same point here, what you're finding is that the Rossby wave is squeezing this low sea level further towards the equator. So as you squeeze low sea level towards the equator, it means your main change in dynamic height is occurring near the equator. Again, Coriolis force is smaller there, so your transports become larger. So what this is doing is actually increasing the transport of the NECC, in that part of the ocean during that period. And we can see, well, you can see this slightly. This is this point where we're getting a lump, high sea level at the equator, 180 east. And we can see the region of low sea level, which tends to move towards the equator during this period. And what you see, if you look at the vertically integrated transport, this is not above 28 degrees or anything, this is the total. A lot of noise due to the effects of instability waves, even reversing the current at times. But again, you see this tendency of the current to move down towards the equator during this period, the passage of this Rossby wave. That's the figure I've just shown you. And if I actually look at integrate the transports in here, I find that instead of being around 20 sphere drops or so, this can go up to 30 and 40 and even more during that period. So what it's tending to do is you've got the NECC, which normally is losing a lot of heat. Here, we're not only not losing heat because the tropical instability waves are smaller, the actual transport in the current is stronger, so it's pulling more water across the Pacific anyway. How are we doing for time? Okay. So I'd like to go through what I call a classical El Nino. This is going through the 3/4 of 1982. This is starting in the spring. We've got winds, one of these is winds, this one's got winds on the top, I think. Easterly winds in this region, Ekman suction here, giving us cold water there. What's notable is when you turn that off, again, I should have said this earlier, but when you turn that off, the main thing that happens is you get water from about 27 degrees flood in. What people will say is, oh, we had 21 degrees, we've gone up to 27 degrees, show an anomaly, that's a 6-degree anomaly. And on a global picture, that looks huge. So people tend to say, oh, the 6-degree anomaly is causing the El Nino, or somehow, in some way. It isn't. It's the fact that you increase the temperatures here up to 26 degrees at any point is really irrelevant. It looks impressive, but it's a result of the El Nino, not the cause of the El Nino. And I think a lot of the problems have been that people have confused the effect of the El Nino with causes of the El Nino. Okay? And so I think, you have to be very careful about cause and effect. And I hope I have been. The Rossby wave started at this point, but come midsummer, it's extending all the way across, and you're starting to get this quite strong North Equatorial Counter Current, which wasn't there in the spring. Along the equator, there hasn't been all that much of a change, but I think that's the main features there. We come to the autumn, which you've seen quite a lot of already. This warm water has been taking across, is now in the Central Pacific following the NECC. You've still got the tropical instability waves, but you also find that the Rossby wave is starting to move across. And around this area of the high sea level in the Pacific, you're also getting reasonably strong currents. So again, that's helped to bring water across. Now this effect has been identified previously by a Chinese guy, Kug, I think it is, K-U-G. So I have to call it something like Kug's High or something of that sort. But he's the only person who's really mentioned it. And then come December, you've got hot water all along the Pacific. What you find is that this feature has actually moved, and what it seems to be is actually, this is the southern summer, middle of the southern summer, and this is essentially, a lot of this is not so much advection, because there has been no advection. This is summer heating in the southern hemisphere. So the fact that we've got low winds appears to mean the surface temperatures in that region can become higher. And to see that essentially these Rossby wave effects right across the ocean there. So the annual Rossby wave, you can probably read this faster than I can. So it starts in the Eastern Pacific, it arrives in the West Pacific around June. The slower moving waves further north, it deepens the trough, I said, it moves it towards the equator, increases the strength of the NECC, and it means the warm water starts moving east in mid-year and arrives off South America around Christmas and the New Year. I'll make that comment out again. Sorry, that's now, I want to have a go at westerly wind bursts. I've had a bad morning, so I might as well have a go. Normally, people talk about westerly wind bursts causing the El Nino. Now, this is the wind bursts in the reanalysis, and I'd like to compare it with the actual sea surface temperatures. And what you find is the wind bursts only occur over warm water. So once the water has been warmed, once you've got an El Nino started, then you can get a westerly wind burst. It doesn't, and what they do is they drive Kelvin waves. You look at equatorial sea level, you can see the Kelvin waves going through. These are these regions of high sea levels going through. But there seems to be absolutely no correlation between these westerly wind bursts and the movement of the warm water in the Central Pacific. So, and what you expect is once you've got warm water, you're going to have some sort of convection north and south of the equator. That tends to give you anticyclonic flow in both hemispheres. And anticyclonic flow always gives you westerly winds along the equator. So you can actually say that it's quite likely, I haven't proved it, but it's quite likely that this warm water is actually causing these westerly winds in this region. And they do produce that current, and they do seem to produce that region of high sea level in the Central Pacific, but they don't seem to be moving they don't be responsible for moving the main region of warm water across the Pacific. That is the NECC. Although, admittedly, near the equator in this region, they are moving more water towards the east. The other thing I wanted to talk about was you get El Ninos, you get things happening in other years. And certainly in 1997-98, there seemed to be some event that started early in the year. And I was wondering what caused that, because as far as I knew, there was no warm water, but why did we get a westerly wind burst there? And I had a look in detail at this is the average over, I think it's something like 2 or 3 months. The average winds in a normal year, and you can see this is rainfall is one of them, and the winds you can see as well. And in this sort of early the years, the southern ocean is getting, the southern hemisphere is getting warm. You've got the intertropical convergence zone in the north, raining away, and you've also got this warm patch in the South Pacific with lots of rain as well. What seemed to happen in 1997 is that the amount of convection in the South Pacific was much higher than normal. And though over a period of 2 to 3 months, there was a wind field crossing the equator along the coast of New Guinea. Now, New Guinea is a high island and lots of mountains, and you can get a flow there, a little bit like they get in the Indian Ocean. There's I forgot what it is, there's a jet along the African coastline, which also allows air to cross the equator. And it looks as though that what was happening during this period is we were getting air crossing the equator systematically during those months. Now, the equator runs just north of New Guinea, along this line here. And what that really means is that during this period, there was a westerly wind, not due to convection. They're not wind bursts, but they were steady winds due to the large-scale convection in the South Pacific. And that does seem to have brought warm water part of the way out into the Pacific at that point. So if you like, it was starting an El Nino due to these winds crossing the equator. But that sort of thing by itself couldn't get heat right across the equator, and it really depended, that year you had a Rossby wave coming in from the east again, which sort of got things going in the middle of the summer. So there are other mechanisms. What I've talked about is not the only mechanism, but it looks as though mechanisms of events like this, which seem to occur fairly often around early in the year, January, February, March, when the South Pacific is warmest, can start El Ninos, these smaller El Ninos at other times of year. Right. So conclusions. Really, these are conclusions from the model, and I guess what they are is hypothesizes about what's really happening in the real ocean. And I'd like to be stronger than that, but I'm going to be careful. Most of the eastward transport in these strong El Ninos is occurring in the NECC. I haven't really looked at detail in the more average El Ninos, but I suspect that the NECC has an important role there as well. We've identified 2 oceanic mechanisms. There's not a tendency of these, people say, oh, the atmosphere drives the ocean and there's a coupled system and then the El Nino occurs. Actually, it depends, I think, on 2 oceanic mechanisms, which, to be honest, we don't know a lot about. There's still argument about what generates the tropical instability waves, and there's some arguments, about the formation of the Rossby waves. So we've got 2 mechanisms. We've also got mechanisms which can help start or act during the development of the El Nino. And they've come out of this model 1. What have I done there? So these are the 2 mechanisms. The Rossby wave. Okay, no, sorry, I've pushed the fingers to, let's go back. Okay. So mechanism 1 was this reduced dilution of the NECC, the longitudes of the atmospheric deep convection. That's essentially the warm pool. And this mechanism 2 is the stronger than normal annual Rossby wave. And then the mechanism 3 is this thing due to CUG, which is that the increase in sea level at this point can generate an extra strong current. That's the mechanisms that are occurring during the El Nino. You've still got to start it, and I think in the strong El Ninos, the key thing is this Rossby wave arriving in the Western Pacific, and that actually kicked the process off. It got warm water away from the coast into a region where it could then, convection could start, winds would drop, tropical instability waves would die away, and the process could continue. The second mechanism is the South Pacific warm fall can generate winds and can start something going, and it certainly seemed to have happened in 1997, but I haven't found another year. Well, I haven't gone into it in detail in other years. And the westerly wind bursts, I said I'd have a go at it. I don't think they have any serious impact. And that's it. So thank you very much.